In this video, we're going to look at the strength of carbon-hydrogen bonds, and then go ahead and talk about how their strength changes their reactivity in radical reactions. So let's start by looking at this table, which I took from the book. This gives you the dissociation energy of a variety of different kinds of CH bonds. Now, what these mean is the following. Here, secondary. This is secondary CH. Says it has a dissociation energy of 410 kilojoules per mole. That means that it takes 410 kilojoules of energy to break this bond this way, and we break it what we call heterolytically, where each atom gets one electron. So here's this propane, and if we break propane CH bond here, we get the secondary propyl radical and hydrogen radicals, and that takes 410 kilojoules per mole. Now, the interesting thing is here is which ones are the strongest, and we'll see that some bonds are, of course, stronger than others. So secondary is 13 kilojoules. A radical is 13 kilojoules weaker than that of the primary, which means that the primary bond is that much stronger. So primary CH bonds are stronger than secondary. And if you look through this list, I mean, what are the strongest bonds? Well, the strongest one that I see in this list is phenyl. Phenyl is 464. That's a very strong bond. Actually, alkynyl is the strongest. Why is alkynyl the strongest? Because it has the most S character. This is an sp hydrogen, so it's 50% S, so that's the strongest one on the list. Phenyl is sp2, it's 464. Here's vinyl, which is a hydrogen on a double bond. It's 431, also very strong. The sp3 ones are all weaker, but as you see, they vary in strength as well. Now let's look at this a little bit closer. It says that 13 difference is 13 kilojoules per mole a big number. So primary is 13 kilojoules stronger than secondary. So how much difference does that really make in chemical reactivity? 13 kilojoules doesn't really sound like much, but it is 13. Is that 13 kilojoules? Is that a big number or a little number? If you haven't thought about these things, you probably don't know. So how can we take that 13 kilojoules and convert it to something which is more familiar? It makes more chemical sense. Well, the answer is, let's go to an equilibrium. And so what would be the equilibrium constant between this? Is it basically the 13 is delta H for this reaction. So, and it turns out entropy isn't very important. So this is delta H, and so that's essentially the delta G for the reaction. So how could we go from delta G of 13 to an equilibrium constant? Okay, well, we're going to do this, and we have to do something horrible. We have to think about general chemistry. So back in general chemistry days, you actually worried about thermodynamics, and the most important equation here is delta G, the free energy of the reaction, was minus RT of the log of the equilibrium constant. Now that's natural logarithm, and so how can we use this equation without messing up our minds too much? Well, let's do some simplification. Let's get rid of those natural logs and go to base 10 logs, which make a little bit more sense in my mind anyway. And to do that, you need this 2.3 constant. Then we can look up the value of R. We can look up, and we consume a temperature of 298, which is 25 degrees Celsius, which is kind of a standard value people like to use. And we can combine all those constants, and we'll get this new equation, which simply says delta G is equal to minus 5.7 kilojoules per mole. Now, that's very nice, or we can turn around and write it this way. Now, delta G is, in our particular case here, the delta G is 13. So 13 kilojoules per mole divided by minus 5.7 kilojoules per mole is minus 2.3. So minus 2.3 is equal to the log of K equilibrium. And so then we can turn this around. K equilibrium is 10 to the minus 2.3 power, or 0.005. That's a very small number. That means it's less than 1 in 100th is going to be in terms of products, in terms of an equilibrium. Now, this all is very confusing. The only thing I want you to really remember from all this slide, don't forget all the derivation, but remember this, that 5.7 kilojoules per mole is a power of 10. Okay, this is a power of 10 because if K equilibrium is 10, delta G is 5.7 because the log of 10 is 10, is 1. Log of 10 is 1. So 5.7 is a power of 10 in equilibrium constants. And that's a really easy calculation to do. And if it's too complicated, round it off and call it 6 and say 6 kilojoules is a power of 10. And that's a really good number to know. So 13 is divided by 6 is a little bit more than 2. So this is, it's easy to figure out these equilibrium constants. Okay, so let's go back. So 13 kilojoules per second is a big number if you think about it in terms of the equilibrium constant, because we just calculated this equilibrium constant and it's 0.005. That means there would be very little primary if these two are in equilibrium. Now, normally they're not in equilibrium. Why are they not in equilibrium? Well, this one's so much more stable is that kinetically you probably aren't going to make the primary one. But if you could make equilibrium, it's very little primary would be expected. It really prefers the secondary under those circumstances. So let's look at some other comparisons. So now we're going to actually do a reaction. And in this reaction, we're going to talk about the mechanism of this in the next video. But in this reaction, basically a bromine radical abstracts the hydrogen to form a radical. And sorry, this thing is jumping around. So what we want to do is we want to look for the weakest bond because that's the hydrogen which is going to be given up. And so here's our chart. So we just have to look at these various kinds of hydrogens as this molecule and then look at the chart. So what do we have? We have the possibility of primary radicals, these methyls. We have secondary radicals. We have tertiary radicals. We have a benzylic radical, and then we have phenyl radicals. So the question is, which of them on the chart is the smallest number? So you just look through this, find the smallest number. See if you pause the video for a second and see if you can find which of these numbers of the various possible ones is the smallest. Well, okay, which one's the smallest? Well, benzyl, 372. Okay, look at that. That's the smallest number of the various ones which are in this particular molecule. It's not the smallest in the table, but it's the smallest of the choices which are in this molecule. So which reaction do you make? What would you expect to be the favored one? Reaction D. So if you reacted this compound of bromine, the compound you'd expect to form is the one where the benzylic radical undergoes the reaction. So which is the least favored? In other words, which is the strongest bond? So if you looked at all this, we kind of did this before. What are the strongest bonds in this whole table? Well, the sp hybridized carbon of an alkyne. Next is the phenyl with an sp2 hybridized hydrogen. So phenyl is the worst. So the worst is choice E. You're not going to form choice E. That's the worst by far. Okay, so let's do another one. Now I have an allyl system in here. Which one's going to be favored now? This one's a little bit trickier. So I mentioned already this is an allyl, so I've kind of given it away. So let's look at allyl here, 364. So the allyl bond is actually weaker even than the benzylic one. So we're definitely going to form an allylic, do an allylic bromination. So now here's our double bond. The allylic positions are the methyl to the left or this methylene to the right. That's going to give us our allyl radical. Now, which one is actually favored though? So if we did this one here, which would be C, this is an allylic position, but we could also do E down here and go to that one. So which is better, C or E? Well, it turns out the allyl radical is just like a double bond, is more stable with more substituents on it. So having an allyl radical in the middle of the molecule here is better than at the end of the molecule down here. So C, it turns out, is better than E. And so C is better than E. Now, if that was all there is to it, we'd say, well, that's pretty simple. But allyl, of course, has an extra wrinkle. Is that C is the correct answer, but there are two products, and if the other one is not E, what's the other one? Well, the key thing to remember is that in this reaction mechanisms, as I mentioned, there is an allyl, a radical allyl, an aldol radical intermediate, which means you can have delocalization. And the delocalization gives you B as well. Now, how does that work? Well, it's just like this. If this were the C position, this is in total another resonance structure. Is simply putting the radical center on this other carbon over here. This would give you B. So this would give you C. This would give you B. So there are two products. And as I say, we will talk about the mechanism of this reaction in the next video.